Welcome to the Explainer. You know, sometimes science is like a great detective story, and today we're on the case of the atom. We're going to follow the clues one by one that completely unraveled the mystery of what matter is actually made of.
Okay, let's just jump right in with something that might blow your mind. What if I told you that everything you can touch, the chair you're on, the device in your hands, even you, is actually 99.9% empty space? Sounds crazy, right? Well, that's the truth. And figuring that out was like solving a massive scientific mystery, one that took a handful of brilliant minds to crack piece by painstaking piece.
So, where does our investigation begin? Well, for a long time, the main theory was pretty simple. People thought of the atom as this tiny, solid, unbreakable little ball, like a microscopic marble. But then a clue popped up, something you've probably seen yourself. You know how if you rub a comb through your hair, it can suddenly pick up little bits of paper? That static electricity, that was the first hint that something more was going on inside the atom. It wasn't just a solid ball, after all.
All right, so let's meet the lead detectives in this whole atomic mystery. We've got John Dalton, J.J. Thomson, Ernest Rutherford, and Niels Bohr. Over just a few decades, these guys completely turned science on its head. Each one made a discovery that built on the last, and sometimes completely shattered what everyone thought they knew.
So, for quite a while, John Dalton's model, the solid, indivisible sphere, was the main theory. And look, it was simple, it was elegant, it explained a lot of things, but it just couldn't explain that static electricity thing. That simple comb and paper trick was like a piece of evidence that didn't fit. The case against the indivisible sphere was starting to get stronger.
And then, boom, J.J. Thomson discovers the electron. This was the moment the case really cracked wide open. He came up with a whole new model. Forget the solid ball, he pictured the atom as this sphere of positive stuff, kind of like a blob of pudding, and scattered inside were these tiny negative electrons. They called it the plum pudding model, and it was the very first time we got a real peek inside the atom.
Okay, so the plum pudding model was a huge step forward, but it had one big implication. It suggested that the atom was kind of soft and mushy all the way through. So our next detective, a guy named Ernest Rutherford, decided to put that to the test. And the experiment he came up with, well, it was going to blow that plum pudding idea to smithereens.
Rutherford's plan was pretty brilliant, really. He basically set up a tiny particle cannon. He was going to fire these little positive bullets, called alpha particles, at a super, super thin sheet of gold foil. I mean, we're talking just a few atoms thick. Now, if the plum pudding model was right, if atoms were just soft blobs, these alpha particles should have just zipped right on through, no problem, like shooting a BB gun through a watermelon. But what he saw, it was just astonishing. I mean, yeah, most of the particles did go straight through, just like he thought, but a few of them were deflected, knocked off course a little bit. And then came the real shocker. A tiny, tiny fraction, like 1 in every 8,000, didn't just get deflected. They bounced straight back. It was like they hit a solid wall. This was the smoking gun, a totally game-changing clue. You know, Rutherford himself said it best. He said it was as unbelievable as if you fired a 15-inch naval shell at a piece of tissue paper and it came back and hit you. Just think about that for a second. There was absolutely no way a soft pudding atom could do that. Something tiny, super dense, and powerful had to be hiding in there. The plum pudding model was officially dead. What Rutherford had found was the atomic nucleus, this tiny, dense, positively charged center of the atom. And this led him to a whole new model, the planetary model. You've probably seen it before. You've got this massive positive core, the nucleus, and then these tiny negative electrons orbiting it, kind of like planets going around the sun. And this model explained everything. The particles that went straight through, they were just passing through the vast empty space of the atom. The ones that bounced back, they had made a direct hit on that tiny, dense nucleus. So, case closed, right? Not so fast. Rutherford's model, as brilliant as it was, had a huge, fatal flaw, a really big one. According to all the rules of physics they knew back then, his model just couldn't exist. It should have self-destructed in a split second. And if that were true, all matter everywhere should have just collapsed. Here's the problem. The physics of the day said that any charged particle moving in a circle, like an electron orbiting a nucleus, should constantly be giving off energy. It would be like a tiny light bulb that's always on. As it loses energy, it would slow down, and its orbit would decay until, wham, it spirals right into the nucleus. This would happen in less than a second. So the new puzzle was massive. If the planetary model is right, why are atoms stable?
Why don't we all just collapse into dust?
And this is where our final detective, Niels Bohr, enters the picture. He came up with a solution that was both simple and revolutionary. He basically said, what if electrons just don't follow the old rules? He proposed that electrons can't just orbit anywhere they want. They're restricted to specific fixed orbits, or what we call energy levels. Think of it like they can only live on certain streets in a neighborhood. They can't build a house in between.
And here's the kicker. As long as an electron stays in one of those special, allowed orbits, it's perfectly stable. It doesn't lose any energy. It can jump from one orbit to another if it absorbs or releases just the right amount of energy, but it can never, ever exist in the space between the orbits. And just like that, this brilliant idea solved the whole collapse problem. The atom was saved.
Okay, so we've got a nucleus, and we've got electrons living in these specific shells or orbits. The next big question is, how are they organized? Is it just random? Nope. Turns out there's a very clear set of rules for this atomic architecture, and these rules are what make every element in the universe behave the way it does.
Think of these electron shells like floors in a building. There are strict rules about how many people, or electrons, can be on each floor. The first floor, the one closest to the nucleus, is pretty small. It can only hold 2 electrons. The second floor can hold 8, the third can hold 18, and it just keeps getting bigger the further you go out. There's a set capacity for each one.
And the filling rules are pretty simple too. Electrons always fill from the inside out. They take up all the spots on the first floor before anyone moves to the second, and so on. But here's the most important rule of all, the one that drives all of chemistry. An atom is happiest, it's most stable, when its outermost shell is completely full. That's its goal.
And you might be thinking, okay, rules for electrons, neat. But this isn't just some abstract diagram for a textbook. This structure is everything. It is the absolute key to understanding all of chemistry. It's the reason why some elements are super reactive and others are totally chill. And it explains exactly how they bond together to make, well, everything.
This whole idea leads us directly to something called valency. The best way to think about valency is like an element's personality. Is it desperate to give away an electron? Is it looking to grab one from somebody else? Or is it willing to share? It's all about what an atom needs to do to get that stable, full outer shell. And that number, its valency, basically determines who it's going to be friends with in the chemical world.
Let's look at sodium. It's a perfect example. If you map out its electrons, it has 2 in the first shell, 8 in the second, and then just one single lonely electron all by itself in the outer shell. Now, to get stable, it needs a full outer shell of 8. So what's easier, trying to find and grab 7 more electrons or just getting rid of that one lonely guy? Yeah, it's way easier to just give it away. And that's exactly what sodium does. It makes it super reactive, always looking for someone to take that extra electron.
And because it wants to give away that one electron, we say the valency of sodium is 1. Simple as that. Its entire chemical behavior is defined by that one little electron on the outside.
So, we've talked a lot about electrons and how they define an atom's personality, but the nucleus has its own secrets too. This leads us to the idea of isotopes. See, you can have different versions of the same element. They'll have the exact same number of protons, that's what makes it that element, say carbon, but they can have a different number of neutrons. This means they act the same chemically, but they have different weights. And isotopes aren't just some weird trivia for science class. They have some incredibly powerful and important uses in the real world. You've heard of uranium-235, right? That's an isotope that fuels nuclear reactors. And in medicine, isotopes like cobalt-60 are used in radiation therapy to fight cancer, while iodine-131 helps treat thyroid problems. They are literally life-saving.
So, there you have it. This amazing scientific detective story took us from a simple, solid little ball all the way to this complex, miniature solar system inside every single thing. We uncovered the hidden rules that run the entire universe of chemistry. But you know what's funny? In solving this one massive mystery, these scientists accidentally opened a door to an even deeper, weirder, and more mind-bending world, the world of quantum mechanics. And what happens down there? Well, that's a whole other case for another time.